Welcome to our last set of experiments for this semester. We're going to be looking at the qualitative analysis of selected cations. And what has been done is we have a set of cations that have very similar properties. And you'll discover what kind of properties those are in a minute. The group 1 consists of silver, lead, and mercury, and for obvious reasons we're not going to be working with those, but we are going to be working with group 2, group 3, and group 4 cations. What we're going to be doing is separating these cations and then identifying them. Okay, so if I give you a mixture of bismuth and cadmium, copper, and tin, and you don't know what it is because it just looks like a pale, clear blue liquid, you're going to have to separate out each of these individually and then identify them. So that's what we're going to be doing. And how do we do this? Well, the way that we're going to be separating them is primarily by their solubility. By their solubility. In other words, we're going to make some precipitates, some ionic compounds that don't like to dissolve very much. We're going to be making some precipitates, and by adjusting the conditions of those precipitates, we're going to be allowing certain ones to dissolve and keep certain ones as a precipitate. And there are going to be a couple other things that we do that will also help us to separate these ions, and finally to identify them. So as we talk about solubility, we're going to be looking at the solubility product constant for a number of these cations and their sulfides. Okay, we're primarily going to be working with sulfides. Remember, sulfides have the anion S2-. So we're going to be looking at the solubility product constant, and this is an equilibrium constant, solubility product constant. Now, what is this? Well, this is a way of measuring, way of determining how soluble, how easily dissolved a particular ionic compound is. So, for instance, if we have silver sulfide, which we're not going to have, but let's go with that. Silver sulfide is Ag2S. Now this sets up an equilibrium with its cations and anions. So 2 silver plus, and this is aqueous, and a sulfide ion, and this is also aqueous. But notice the silver sulfide itself is not aqueous. This is a solid. So this is our precipitate, and this would be our solution in which the ions were broken apart, were hydrolyzed by water. Okay? So what we're going to be doing is varying conditions so one or the other is favored. If we want to separate out silver sulfide and everything else is in solution, we're going to shift the equilibrium such that silver sulfide is favored and it'll precipitate out. Or say we have a whole bunch of precipitates and we want to be able to separate silver out, then we would have to shift the equilibrium towards the products. So that's what we're going to be doing. And the KSP is simply the equilibrium constant for this particular type of equilibrium. So it's going to be silver plus squared, because of the 2, and times sulfide. And sulfide has just the coefficient of 1, so it's to the first power. Now notice we have no denominator, and that's because this is a precipitate. It is a solid. So we treat it as if it has the concentration of 1. All right, so that's a little bit of the theory behind what we're going to be doing this week. So let's take a look a little bit further down this table. I'm actually walking you through the pre-lab discussion so that you can focus on it, glean from it what you need to before you do the pre-lab. Now, one thing that is going to be really important is that our group 2 cations, and these are bismuth and cadmium and copper and tin, these group 2 cations form extremely insoluble sulfides. That's going to mean that their KSP is extremely small. Very, very few of these compounds that are formed by bismuth and sulfide, cadmium and sulfide, copper and sulfide, tin and sulfide, very, very few of those are going to actually dissociate into the ions. So we have, again, here's bismuth sulfide and cadmium sulfide and copper 2 sulfide and tin 4 sulfide. These are very insoluble. Now, okay, that's fine, but how is that going to help me separate them from maybe the other cations, like maybe are in group 3 or group 4? Well, what this means is that if I have a solution in a test tube that has all of these different cations in it, if I add just a tiny amount of sulfide to it, and I'm talking tiny, then these 4 will precipitate out and the rest will stay in solution. Once we get group 2 to precipitate out and group 3 and 4 are still in solution, we can centrifuge, which is going to allow us to separate according to density. We'll end up with a test tube that has a pellet in the bottom of the solids and what's called the supernatant, and that's the solution. Okay? So we will centrifuge it, get this pellet and this supernatant, and we will decant the supernatant. So we end up with 2 test tubes, one of which has the pellet in the bottom that we'll be working with, and one of which has the solution. Okay, so that's one way in which we'll be separating out immediately our group 2 from group 3 and group 4. Well, this is all very fine and nice, but we need to figure out, if we're going to do this, how we're going to get this tiny amount of sulfide into this aqueous mixture. Well, usually this is done with something called hydrogen sulfide, and I've mentioned this in class before. This is a toxic gas, smells like rotten eggs, is extremely toxic, but we just don't want that flying around a general chemistry laboratory, so instead we're going to start off with a solution called thioacetamide, and this thioacetamide, once you dissolve it in water, gives us, when you heat it, anion and a cation and hydrogen sulfide gas. But this hydrogen sulfide gas is already dissolved in the water, so it's not free in the atmosphere. Okay? The lab is going to smell a little like rotten eggs, but it's certainly not enough to hurt you. Now this hydrogen sulfide, as you'll notice, because we write it as H2S, that's a weak acid, and it's extremely weak acid, and it can lose 1 proton, and it can lose a 2nd proton. So this is a 2-step process, but in fact, hydrogen sulfide does just exactly that, leaving the sulfide that we need in order to make the precipitates. All right, so when we combine these 2 equations, what we come up with is hydrogen sulfide plus water gives us sulfide and 2 hydronium ions. Okay, so again, this is an equilibrium, so we can write the K for it. Okay, in this case it would be the Ka, but we've labeled it K hydrogen sulfide. And you'll notice hydronium ion squared times sulfide divided by H2S. This is aqueous. So notice how small this is, 1.3 times 10 to the minus 20th. Yeah, you don't get a lot of sulfide out of this, but it's going to be enough. Now, one thing I do want you to notice, and it's a very important point here, is that the sulfide concentration is indirectly proportional to the hydronium ion concentration. In other words, as the hydronium ion concentration drops, the sulfide ion concentration is going to increase, and vice versa. Well, how do we detect this? We can measure the pH. Obviously, as the hydronium ion concentration drops, the pH actually rises, right? So as the pH rises, the sulfide ion concentration rises. But remember, we said way back at the beginning, for group 2, these are very insoluble. We just need a tiny little bit of the sulfide concentration. Otherwise, group 3 and 4 are both going to precipitate out too. So we want to minimize the amount of sulfide. Just a little bit of sulfide, the least little bit of sulfide we can get will allow us to precipitate out group 2. So in order to get a low amount of sulfide, we have to have a low pH. Okay, so that's what we're going to be working with in our group 2 study this week, is really low pHs. All right, so let's take a look at how we're going to break this down. Remember, we've got bismuth, and we've got cadmium, and we've got tin, and we've got copper. And now that we've separated this group 2 from group 3, 4, we have to separate these cations from each other. Now remember, they're all in their sulfide states. And here, the first one we're going to look at is tin sulfide. And this is actually a very easy one to separate out. And why is that? Well, tin sulfide is the only cation. It's the only ionic compound of the bunch of group 2 that will dissolve in base, but specifically in KOH. This is a very specific base that you need to use. Only tin sulfide will dissolve in it. So again, you've got your precipitate here, right? You've got all of these sulfides in the bottom of the test tube, and you're going to add in some KOH. And all of a sudden, you're going to have a solution that has the tin in it, and the tin is existing as what we call a complex ion. Now, a complex ion simply is an ion. It's a polyatomic ion, but that has a metal core, and this is usually a transition metal core, and ligands surrounding it. Now, these ligands can be charged or they can be uncharged, but this combination of the metal core and the ligands, the overall species has a charge. Now, the thing that's cool about these is they're usually highly colored, and they increase the solubility of certain precipitates. So as we add KOH to this solution, all of a sudden our tin is in a complex ion state and it's aqueous. So now our tin is in solution, and we can centrifuge this and separate out the tin from the copper and cadmium and bismuth. So that's our first step. Okay, we're starting out with a super acidic set of group 2 sulfides. Then we're going to add KOH, and what happens as a result to the pH? The pH increases, okay? But we also form our tin complex ion. Separate them, and we move on. Now, what you will be doing, and I'm not going to talk about this, you can read it in this particular pre-lab section. The tin will then be reacidified and the compound reformed so you can actually identify it. And it'll form a mustardy yellow solid. Okay, so now we've identified tin, and we're going to move on with our cadmium and bismuth and copper. Well, the next one we're going to separate is going to be cadmium. And to separate cadmium, you drop the pH. And when you drop the pH significantly of cadmium, you have to use HCl because we need that chloride. The cadmium's going to form a complex ion with 4 chlorides around it. Overall charge 2-. Now again, the cadmium is going to form a complex ion, and our copper and bismuth are still precipitates. So again, you're going to centrifuge and separate. Now you're going to have to identify that cadmium, and the way you identify the cadmium is again to change the pH. And actually we're going to be making a different compound to identify for cadmium. Once we centrifuge and separate and identify cadmium, then we're finally going to be working with our bismuth and copper. At this point, the bismuth and copper are still sulfides, and we're going to add ammonia to them. Notice not a potassium hydroxide or sodium hydroxide, specifically ammonia. And this is because we're not trying too hard to make it more basic, but we're going to form this lovely, and it's bright blue and beautiful, and you've actually seen it before, copper tetraamine complex ion. Beautiful dark blue, almost the color of this pen, a little darker. The fact that you have made the solution basic is going to take your bismuth and create a white precipitate. So you're actually going to see bismuth hydroxide as a white precipitate, and in the same test tube you're going to see copper tetraamine complex ion as a dark blue solution. So this is what you're going to be doing. Let's follow the pH here. We started with a very low pH to form our sulfides. We then raised the pH with KOH in order to separate out tin. After we separated out tin and identified it, we dropped the pH, but specifically with HCl. And that allowed us to separate out cadmium as a complex ion. Once we had separated out cadmium and identified it, then we're going to take the pH back up for the remaining solution. Taking it back up using ammonia. The ammonia serves two purposes: to make a basic solution so that bismuth hydroxide can precipitate out, and to make a copper tetraamine complex ion, which is a blue solution, which allows us to separate and identify these last two cations. So by moving the pH all over the place and by using centrifugation, forming that nice little pellet of precipitates on the bottom, and then decanting the solution off of that, we're able to systematically separate these various cations that have formed fairly insoluble sulfides at this very low pH. So I hope you can kind of see what we're doing here by taking our pH up, down, adding different things, KOH, HCl, NH3. We're able to take the sulfides that we formed way back at the beginning and one by one separate them in tin and cadmium and copper's case, all three of them, by adjusting the pH and adding different compounds to it, we were able to form complex ions, which allowed us to separate first tin, then cadmium, then copper. Once we had those complex ions, we could take them back and ID the compounds. And with copper, we didn't have to take it anywhere because the copper tetraamine dark blue solution is, in fact, the identification for copper. So that's what you're going to be doing this week. Mr. Proetta is going to give you lots and lots of help in the practical aspects of this. Now that you should understand what we're doing, we're changing the solubility by adjusting the pH, by adding certain compounds, changing the solubility so that some things are soluble and other things aren't, which allows us to separate those cations and then ultimately to identify them. So what you'll be doing, you're first going to be given a group 2 solution, and then you'll be given a group 3-4, both 3 and 4 combined solution. And finally, you'll get what's called a general unknown. And the general unknown has select cations from group 2 and from group 3 and from group 4, and you have to identify each one of them. And your identification of these cations is basically your grade, or at least a large portion of your grade, for the next 4 weeks. So I will see you soon in lab, and yeah, work hard on that pre-lab. Make sure you read this section really carefully, and we'll see you soon.